Um, in the same way that Newton did research with the force of gravity, Coulomb did research on the force between two fixed electric charges. So Newton looked at how masses apply forces on each other, F equals big G, m1, m2 over r squared. Coulomb found that electric force equals, leave a small space, Q1, Q2 over r squared. But just like for gravity, we needed big G as a constant to get an answer in newtons. We need a constant here. It's little k is the letter that we use. K from the German word constant. And little k is on your formula sheet in the data section. Can you all find what little k is? Sean, you want to go look on your formula sheet somewhere near where the elementary charge is. What's little k as a number? Times 10 to the, much nicer to type than 6.67 times 10 to the negative 11. 9, scientific notation, 9. I can hit that really quick with my thumbs. 9 times 10 to the ninth, and then the units would be, I don't know, something, 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 something. What gives you newtons in the end? Sorry, 9 times 10 to the what, Gerard? What was gravity? 6.67 times 10 to the what? That means electric force, it is 10 to the 20th power stronger than gravity. Electric force is 10 to the 20th power stronger than gravity. Gravity is by far the weakest of the four fundamental forces, by far. Q1 is the charge of the first object in coulombs. Q2 is the charge of the second object in coulombs. And then D or R is the distance between the charges in meters. By the way, what equation does this look an awful lot alike? It really looks similar to gravity. Charges come in two types, positive and negatives. The fact that there's two types of charge has certainly made physicists wonder, are there two types of masses? Is there such thing as a negative mass? Not antimatter, but a mass that would be anti-gravity, that would repel. We don't think so, but it was a nice hypothesis at one point, like, hey, maybe it's out there. Now, this is a scalar equation. To find the direction of the force, we're going to use like charges, unlike charges, attract. And in the right circumstances, you can have enough charges build up that they will jump to another object. They will repel each other. They will jump to another object. If that involves a human, we call that getting a shock. Let me hit pause. So, Coulomb's law. To solve an electric force problem, first thing, you need to express the charges in coulombs. What do you mean? We're often going to be dealing with micro coulombs, you'll see in just a second. Secondly, you substitute the charges and the distance into Coulomb's law to find the force. And then to figure out the direction, we're going to use like charges, unlike charges, attract. Now, technical comment here, if we have unlike charges, if one is positive and one is negative, for example, then the answer we get for the force will be negative. I don't want that. Negative indicates attraction, like unlike charges. It doesn't indicate that the force actually has a negative magnitude. And so for this reason, a lot of textbooks will put absolute values around the Q's. And again, you can go big Q, little q if it's a big charge, planetary charge, little q, satellite charge, or Q1, Q2. I can't remember, did I put absolute values around Coulomb's law on your formula sheet? I did, okay. And this is also my way of making sure you now know what section we're in. We're in the Coulomb's law electrical section. Okay. So let's do an example, example 8. It says find the electrostatic force on an electron in a helium ion. And the radius is 2 times 10 to the negative 11. Okay. Nate, what do they want me to find? That's going to be Fe, which is K, Q1, Q2 over R squared, or K, big Q, little q over R squared. Okay. What's K? Oh, 9 times 10 to the ninth. An easier one to remember if you're lazy and you want to memorize it. It's on your formula sheet, though, but also a way easier one to type on our calculator. Nate, what's Q1? What's the charge in the nucleus? Well, I see 2 neutrons. What's the charge on a neutron? I also see 2 protons, so it's going to be 2 times, it's a proton. 1.6 times 10 to the negative 19. That's Q1. Q2 is going to be the electron. What's the charge on the electron? It's an electron. Same thing but negative, except we said in this formula we're not going to put the negative into the actual equation. Instead, they're unlike. Unlike charges attract or repel. Like charges, so unlike charges, okay, if we need a direction, divided by, and 2 times 10 to the negative 11th, don't forget the squared. What are you going to get for the force? So get your calculators out, just for giggles. Did I type that in right? 9 times 10 to the ninth times, oh, nope, got a typo there, Mr. Dueck. Times, not scientific notation. 2 protons, 1 electron, and because I'm using my scientific notation button, I think I can get away without brackets, but if you're not sure, put brackets around stuff as well. I got 1.152 times 10 to negative 6 newtons. 1.15 millinewtons, if we wanted to go small. No, sorry, micronewtons, not millinewtons, micronewtons. I'm going to go 1.15 times 10 to the negative 6 newtons. That's the force that's holding the electron in place in its shell around this helium ion. Why is it an ion? Normally helium has 2 electrons. We've lost one, so we have 1 electron. Is that a big... First of all, let me pause. Andrew, you get that okay? 1.15 times 10 to the negative 6? Okay. Gerard didn't? Okay, give me a second, kiddo. Pause the video. Is that a very big force? Wait a minute. F equals what? Let's find the acceleration of this electron by going A equals F over M. So go answer button, divided by, and then find the mass of the electron on your formula sheet. I know it starts with 9.11, but I can't remember the times 10 to the... Okay, so go answer button divided by 9.11 times 10 to the negative 31. What's the... Try this on your calculator, Sean. What's the acceleration that this electron is experiencing? This is a huge force. This is what I'm trying to tell you. Gravity is a weak force. Electromagnetic force is very, very strong. As far as the electron is concerned, it ain't going any, like that's a massive force acting on the electron. Oh yeah, you know what? I even did the math right here. I said also, although the force you calculated in example 3 may example 8 may seem very small, we should note that we're dealing with electrons. They have a very small mass. Its acceleration is massive. This is a huge, on atomic terms, a massive force, okay? I like example 9, I like example 9. Example 9 is a nice question. Example 9 says, find the net force and direction on the 1 Coulomb on the 1 microcoulomb charge below. So we have a negative 1 microcoulomb, we have a positive 1 microcoulomb, and we have a negative 2 microcoulomb. First bit of advice I can give you, how many charges do we have? Be stupid obvious, Cormac. Label them. Call this one Q1, Q2, Q3. Because now we have some kind of common vocabulary. Here's what I'm going to do. What does it want me to find the force on? Q1, Q2, or Q3? All of them are feeling a force, but which one does it want me to find the force on? Q1, Q2, or Q3? So here's what I'm going to do. I'm going to find the force from Q1 on Q2, magnitude and direction. Then I'm going to find the force from Q3 on Q2, magnitude and direction, and then I'll add them vectorially. Okay, Oliver, FQ1 comma Q2, the force that Q1 is exerting on Q2, and then the force that Q3 is exerting on Q2. By the way, Q1 is also exerting a force on Q3 and vice versa. I don't care. That's not what the question asked. How do I find electric force? It's going to be K. This one's going to be Q1, Q2 over R1 comma 2 squared. The bottom one is going to be K Q3 Q2 over R3 comma 2 squared. There's my high-tech notation to be organized but not write out a whole paragraph. Are you with me? You're zoning out? So, okay. Ryan, what's K? Do you remember? Much nicer than 6.67 times 10 to the negative 11. Q1, I'm not going to include the negative. I'll use that to figure out the direction by using like charges and unlike charges attract. But I am going to include the magnitude. 1 microcoulomb, 1. What's micro from your formula sheet? 10 to the what? This one might be out of laziness worth memorizing, that when you see a micro, it's 10 to the negative 6, because that's the one I'm going to be using really often. We're going to be dealing with microcoulombs because 1 coulomb is massive. We're going to be dealing with microcoulombs. So it's times 10 to the negative 6. What's Q2? Also 1 microcoulomb. And then R1, at the distance between Q1 and Q2, 20 centimeters. Do I do physics with centimeters? 20 centimeters, how many meters? 0.2, not 0.02. And then, Cooper, don't forget the squared. Okay. Let's crunch that. By the way, you might be able to backspace it. Well, I got the 9 times 10 to the 9th already typed in for the previous question, so I could probably do that and then just delete. Okay, 1 microcoulomb times 1 microcoulomb divided by 0.2. Don't forget the squared. How many newtons is charge 1 pushing with a force on charge 2? Y'all get 0.225 newtons? Direction. So now what I'm going to do is I'm going to pretend charge 3 doesn't exist at all. I want to find the force on charge 2. Charge 1, negative or positive? Charge 2, like or unlike? Unlike charges, what? This is going to get attracted. Let's call that left. Charge 2 is going to get tugged to the left by charge 1. Okay? Like charges repel, unlike charges attract. Let's repeat. It's going to be 9 times 10 to the 9th. Charge 3 is 2 microcoulombs. Charge 1 is 1. Thank you, microcoulomb. And the distance between them is 10 centimeters. That's going to be 0.1 squared. I think I can just backspace, edit, and change a few numbers if you've got a good calculator. I think all I need to do is change that 1 to a 2 and change that 2 to a 1, right? Sean, what'd you get? Because, of course, you're practicing typing these into your calculator instead of sitting passively like a foolish young person. 1.8? Way bigger force. Again, now we need to figure out the direction. Imagine charge 1 isn't part of the drawing at all. Which way is charge 2 feeling a force because of charge 3? Well, again, they're unlike. So unlike charges repel or attract. So it's feeling a force, yes, to the right. Let me erase this. How would I add left plus right? Winner minus loser. Who's winning? More specific as a number exactly? Yeah, the net force is going to be 1.8, take away 0.225, which is what? 1.5, rounded off properly? 1.58 newtons. Is that right, folks? Direction. Who's winning? Yeah. Is it correct? Is it 1.58 newtons? Yeah, okay. Yeah, okay. That rounds. Yep. This trick here, first of all, you'll notice I only have two charges in my formula. If I have more than two charges, I just do them two at a time. And then the fancy word for this is we call this the principle of superposition. I just add the forces vectorially. Okay? Maya, is that okay? Next page. Oh, here's a nice little thought puzzle. It says this. At which point approximately could we place a positive charge so that it would experience no net electrical force, so the force would cancel? It says select one of A, B, C, or D. I'm going to go systematically here. Let's try putting a positive right there. Let's figure this out. Which way will a positive... Oh, you know what? Let's call this Q1. Let's call this Q2 so that we have some kind of reference. Which way will this positive charge feel a force because of Q1? To the left or to the right? Which way will it feel a force right there? Which way will it feel a force because of charge Q2? To the left or to the right? Can right plus right ever equal 0? Okay, let's try location E. I'm just going to go systematically, so let's put one there. Which way would a positive feel a force because of Q2? Because unlike charges attract. Which way would it feel a force because of charge 1? Oh, can left plus left... Okay, you know what? In fact, where is it going to be? Somewhere in... Yeah, it's either B or D. Okay, now let's see if we can figure out. In fact, I would say no. I'll cross that one out right away too, right? Okay, let's put a positive there as a test. Which way will it feel a force because of charge 1? Which way will it feel a force because of charge 2? Which charge is bigger? So this would have a stronger force, although which charge is closer? Which would also have a stronger force. You know what? I think it's B, smaller charge but closer. Bigger charge but further. I think those would cancel out. So B, it says explain your answer using appropriate concepts of physics. I think we've just done that verbally together. That's how I would handle this, though. I would just look at the different locations and use like charges repel, unlike charges attract, and I can figure out an awful lot. So you just want to practice a bit with this and get familiar. It should look kind of mathematically like we're doing gravity again. Okay, so let me see here. Sure, number 1 is good. 2 is good. Gonna sneeze. What's number 2 asking us to find? Oh, you're gonna have to get a Q by itself. Okay, get a Q by... Actually, the charges are identical, so each Q is the same. You'll have Q times Q. What's an easier way to write Q times Q? You'll probably have to get a Q squared by itself and then how to get rid of a squared. In other words, just like gravity, as far as I'm concerned with the electric force equation, if I give you the force, you can find Q1, Q2, or R, or some combination thereof. Okay? Skipping 3, 5 is good. 6 is good. 7 is good. 8 is good. 10 is good. 12 is good. I already nuked the questions that I don't like. 13 is good. Sure, let's try 14. In number 14, what's B asking us to find, Cormac? Electrical force is pulling us in a circle. In the same way you found orbital speed by going gravity is what's pulling us in a circle, it turns out in our model of the nucleus of the atom with the electron in orbital shells, you can certainly model the kinetic energy because electrons are weird, but you can model a V that you could use to figure out the energy by saying electrical force is pulling me in a circle. Okay? Let me pause the video here.